Okay, so let's jump into the material. Last time we had started out this new chapter on stress and equilibrium of deformable bodies. So I think last time basically what I was introducing was how do you determine whether deformable body is going to be in equilibrium or not. And we were trying to draw parallels with what you might have done in your undergraduate by um, drawing free body diagrams of bodies and making sure that sum of forces and sum of moments are zero, right? So that's almost exactly the same thing that we'll do for deformable bodies, but in a more sort of mathematical way, of course, but also since it's a deformable body and since we are going to try to relate these forces that act on these deformable bodies, both external and internally, we're going to try to imagine different pieces or parts of a deformable body, draw free body diagrams of those bodies, and try to find out what are the conditions for equilibrium to hold. So one of the essential aspects of free body diagrams that I was telling you last time was that if you consider any deformable body, you would have some external forces acting on it, some reactions coming from wherever it is being constrained against displacement and rotation. So those would be places where external forces are being applied onto the body. And due to those external forces, the body is going to deform internally and it is going to build up stress internally. But when we draw a free body diagram of the entire body, we only mark the external forces to that body, correct? So I've, for example, for this particular body, after deformation, and by the way, equilibrium will hold in the deformed configuration, not in the undeformed configuration, right? If I have a spring, of initial length L, if I apply a load P, then it's not in equilibrium in its initial undeformed configuration. It's only after deformation that the spring goes down by some amount delta. That so you always write equilibrium equations in the deformed configuration. So here's, for example, an example of a free body diagram. I marked the external forces. These are all distributed forces. These, as I told you, I think maybe some time back, that this is on half of the bottom ring here. I have a distributed force per area, which is a 50 megapascal pressure. There would be reactions coming from the wall. Those are all distributed forces. Again, forces per unit area. But in addition, this body might have some density, might have some weight, of course. So each and every point of that body would be pulled down by gravity or some body force. This is what we call a body force. Body force is something that is a distributed force per unit volume. Okay. So there are two types of distributed forces that I'm showing here: distributed forces per area, distributed forces per volume. And the same is true for any particular small part of a body. You pick any part of that body. If the body is to be in equilibrium, then each and every part of that body must also be in equilibrium. Then you can draw the distributed forces on any imaginary cut, so to speak. And last time I mentioned, we are not really cutting the body. We are trying to just imagine, let's say, a left half and a right half of the body. And we are trying to imagine the forces that might be acting on the left half and the right half independently. What forces is the left half applying on the right half and the right half applying back on the left half. Those are the basic concepts of free body diagrams that I'm sure you are all very familiar with. And once you have the free body diagrams, you enforce Newton's laws and you come up with sum of forces equal to zero, sum of moments equal to zero to determine whether something is in equilibrium or not. We are going to take a similar approach. Go ahead, Vivek.
Would that downward force have an upward reaction?
This one?
The body forces.
That's correct. So there is this reaction which I actually last time I
for the couple, right?
No, that's not just for the couple, but yes. So I guess what you're saying, I should mark body forces here as well. And if, let's say, the density of the material is rho, then and the direction of gravity is, I'll mark that here, let's say E1, E2, E3 out of the plane, then this body force would be acting rho g negative E2. Okay. Rho g is, so each of these arrows, this is a distributed force per volume. So I have density, gravity, and in the direction negative E2, that's the body force acting on is. If you multiply that with the area of cross section, let me say area of cross section is A, then the total volume is A times L. Total mass is rho AL. I'm assuming uniform density, uniform area of cross section for simplicity. And then the total weight of that beam would be rho A L G, and of course that would need to be added here. But in this particular diagram and in this particular shear force diagram, I'm not taking into account the body forces. But you're right that you would all that body, if I were to take into account those body forces, this value here would be P plus all of that, right? P plus the weight. So you would still have the same sort of distribution, something due to a moment, something due to a shear force. And this is another important point here, that each one of those reactions, when we draw those reactions, let's say for a beam theory, we just mark P and ML. These are resultants of some distributed forces. These are not actual point. There are no point forces at all in the universe. Every force is a distributed force. Either it's a distributed force per unit area or per volume. So these P and PL, or these shear force and bending moments, these are resultant forces and moments which are obtained by doing a vector sum and integrating over the area of the cross section of these distributed forces. So these are distributed forces which we are really going to focus on. All right, so back to this. Now to try to come up with equilibrium equations and conditions for deformable bodies, what I'm going to do is to try to consider any arbitrary piece of a deformable body. So I'm considering here some finite piece of the body, let's say this quarter circle out here. And I'm going to further go in and concentrate on a point and a small neighborhood of that point. So there is a point out there in a deformable body. I'm going to consider a small neighborhood of that point. Neighborhood of that point could be any shape. I am considering only like a cubic shape here or a tetrahedral shape here, and I'll come to those reasons in a little bit. But you should be able to imagine that let's say at this particular point, if I consider a small cube, infinitesimal cube around that point, then there are these 6 faces of the cube, and on each of the 6 faces there will be distributed forces per area. Can you tell me where are these distributed forces per area on each of the 6 faces of the neighborhood of that point? Where are these forces coming from? From the surrounding elements, right? So I have some element here, and from the surrounding elements, since the body is in stress, then this particular element is applying forces to the neighboring elements. The neighboring elements are applying forces, distributed forces back onto this particular element. So these forces are all distributed forces per area, the way that I have sort of tried to draw on that as a distributed force. Another important point is that these distributed forces need not be constant. Do you agree? That, for example, when we looked at this bending, the distributed forces per area that we get due to bending, clearly, and due to the shear, these are not constant over the entire area. So from point to point, the magnitude and direction of these distributed forces can be changing. But the good thing is that if I take the limit in which the size of this neighborhood, or the side of the cube or the side of the tetrahedron, when that tends to 0, then we come to an almost constant value. So that's what I'm trying to show in these diagrams, that there are these distributed forces acting on each one of those faces. Those are distributed area forces per area. In addition, I'm also drawing a big arrow to represent some body force that might be acting. And this is all in a small arbitrary neighborhood of a point in a deformable body, which itself we want to make sure that it's in equilibrium. Okay? So this concept of distributed forces per area is going to allow us to introduce this quantity called traction. Now, what most of you relate traction with is actually stress. When I ask, let's say, undergraduate students that what is stress, the most common answer that you'll get would be what? Force per unit area. That is not stress. Okay, force per unit area is not stress. Force per unit area is traction. Traction is what we just defined there on the previous page. These are distributed forces per area, and these are represented with vectors, and these are basically traction vectors, which tell us that the total force acting on some arbitrary area can be obtained by doing an integral. So if I have an area, I have a normal to that area. Let's say this area is a flat plane. Even for a curved surface, that's not a problem. We have a normal to that area, and this traction vector could be pointing in some arbitrary direction with respect to the normal. Traction does not have to be along the normal. So if I have some body, let's say I have this body, inside the body, I have some point here. There is a surface that I'm imagining inside the body. I could imagine infinitely many surfaces in here, but let's say this particular surface. There is a normal to that surface, which of course is perpendicular to that. The traction need not be along the normal. Traction could be acting along the surface. That would be like a shear distributed force. It could be along the normal. That would be a normal traction. And we'll come to all that. But the point is that the traction distributed force need not be normal to that surface. And as I mentioned, the total force will be obtained by taking the traction vector. So, and let's say I consider a small dA area here. So that's dA. And this traction multiplied by this dA, maybe I'll even move that traction onto that dA. So traction acting on this dA, if you integrate that over the entire surface, obviously its traction is a vector. Integral of a vector over the surface will give me a total force. And what does integral mean in this case? Let's say I have this dA, I have this traction, Tn. So the force acting on this dA would be what? Tn times dA, right? Tn times dA would be the force acting on this particular dA. If I consider a neighboring dA, there would be a different Tn times dA on that particular area, right? I have these two vectors now. How do I sum them? Just by vector addition, right? Parallelogram rule or whatever, or components or whatever, right? So that's what this integral means, that when I'm summing up all of these things, I'm getting a total force over the area from the traction. So traction is force per unit area. Stress is not force per unit area. I'll come to what stress is in a little bit. All right. So let me try to derive some relationships related to traction, but go ahead. Before that, we have.
When we define traction, do we assume that, over that complete area A, whatever direction the traction has will be constant?
No, we don't. This entire area could be some big area, right? So what we are assuming is that in the limit that this dA, on this small dA, we are assuming that there is some constant traction. So on different dAs, the traction could be pointing in different directions, but we sum them up just like any vector addition. Okay. All right. So let's try to understand what this traction, what consequences of traction of this definition of traction um, we get on equilibrium. So again, I'm going to go back to that body. Instead of the external force applied on the half ring here, I have some distributed, non-uniform distributed force acting on, let's say, the top face. Again, I get some reactions, some body forces and everything. And in particular, I'll also consider this thin sliver of, this thin slice of that body. So I have a left side body, I have a right side body, and I have a thin slice of that body. If I draw the free body diagrams of these three parts, then I would get this free body diagram of the slice and a free body diagram on the right hand side. Note particularly that Newton's third law holds pointwise, that this particular force or distributed force vector is coming from this slice onto this left part of the body, and the equal and opposite force vector is coming from the left part of the body onto the slice, and this is valid everywhere, everywhere in this free body diagram. So what we'll do now is to try to do sum of forces looking only at the slice of this material. So if I look at the slice of material, I have some traction on this edge on the top, this edge top, that I'm writing as T brackets E gamma. What does that mean? I should have, I guess, made that clear here, that at this point, I have a dA. The normal vector to that dA is being given by n, and with traction, we usually write traction as T sub n. So the amount of traction on a body, especially for points inside the body, depends upon the normal to the surface that you are considering. So T sub n denotes the traction vector there. Similarly, on the top surface of this slice, the normal is pointing, let's say, in the upward direction or the outward direction on that edge. So T sub epsilon gamma, that's the traction coming from the distributed external force up here. There is T minus n. So let's say this face has a normal towards the right of n, and therefore to the left it would be minus n. And traction on the face with a normal minus n is given by this distributed traction. Similarly, traction on the face with plus n is this. We have some body force, and those are all the forces acting on this slice. Now I'll start summing them up. So T sub E gamma, that's this guy, times epsilon ds. Epsilon is the thickness of this slice, right? So this is an area term, dA. If you go all around the slice, the contribution of any traction that is acting on the lateral surface will be taken care of. The way that I have drawn, it seems like the traction is acting only on the top surface, but there might be some tractions on the edges, on the other three edges. That's what this term denotes. Okay, I have traction on the n face normal, and I have traction on the minus n face normal. And I'm doing that integral over the entire cross-section area of that slice. And plus, I have the body force. So I'm saying body force, which is again distributed force per volume. So body force times dV would give me the total force acting on this slice. And what is the volume? It's epsilon dA over again the cross-section area of that slice. So I hope you agree that I've taken into account all the forces acting on this body. This statement right here is nothing but saying sum of forces is equal to 0. Right? I have a free body diagram. I'm going to say sum of forces equal to 0. Now the good thing is that some of these terms go to 0 in the limit when epsilon tends to 0. So as epsilon tends to 0, this term drops out and this term drops out. Both of those terms drop out. The only thing remaining is this. So Tn at any point x on the cross-section area with the positive normal and with the negative normal have to be equal to 0. And what that tells me is that if I combine these integrals, then I get integral over the cross-section area that I'm calling gamma, t sub n at the point x minus, or actually plus, t sub minus n at the point x, any point x on the cross-section, dA equal to 0. That's all that this gives me. And to write out the equal to 0 part is equal to 0, and that should be a 0 vector because we are doing sum of forces which are vectors. Now the good thing to note, one thing to note here is that this cross section that I defined is completely arbitrary. I did not particularly choose one slice, or actually I could have chosen a part of a slice in here and this traction condition would still hold, which means that since this integral goes to 0 for any arbitrary area, therefore whatever integrand we have in here, that must go to 0 for any arbitrary area, which means immediately that t on a face with plus n will be equal to negative of t on a face with normal n. Okay. And this is what is called the Cauchy reciprocal theorem, and it's kind of a restatement essentially of the Newton's third law, which says that forces, if A applies a force Tn onto B, then B applies back a force of minus Tn onto A. That at any cross section, if I am at a point x in a cross section, there is some Tn vector pointing on that cross section. If I look at the opposite face minus n, there will be a negative Tn acting on that. Okay, so that's all that this says. This comes directly from the Newton's third law, and it will be helpful for us in defining this stress tensor finally. So let's figure out what this stress tensor is. In order to do that, we are going to consider now a yet another infinitesimal body. This is just the same body. For example, at a point in a big deformable body, I'm considering a small neighborhood of that point, like this tetrahedron. And the reason why I'm considering this tetrahedron instead of a cube will be clear very shortly. So what we are doing is, in the neighborhood of that tetrahedron, as the size of that tetrahedron, as the edges of this tetrahedron go to 0 in the limit, you can, just like I mentioned, we can replace these distributed forces with equivalent constant tractions acting on each of the four faces. So what does that mean? I have this tetrahedron with four faces. Three of the faces are minus E1, minus E2 going to the bottom, minus E3 going to the back, and then this inclined face. These are the four faces that very similar to the homework problem that you guys did. The tractions on these, I'm labeling them as T sub n, T sub minus E1, E2, and E3 on each one of those faces. And I'm also saying that each one of those normals will be, the tractions on each one of those negative normals will be equal to negative of, so T of minus E3 would be equal to minus T E3, like with the Cauchy reciprocal theorem that we just showed. And there might be some external body force acting on it. And now we are going to try to relate all of these four tractions. Okay, so I have four faces, four different tractions on all of these faces. I'm going to try to relate all of these four tractions with each other and see if we can come up with some quantity which will actually be the stress tensor that relates all of them. So to do that, we'll again do sum of forces for that. So I have drawn that free body diagram. This is my free body diagram. There's no other external forces acting on this infinitesimal piece of material. I hope you agree with that. It's body force, sum of four tractions. And now we are going to do sum of forces on that. And in order to do sum of forces, we are going to use three geometrical identities essentially. that if I have a right angled tetrahedron like this, the one that I've shown, then you can correlate the areas of each of those four faces using the components of the normal vector of that inclined face. So I know that the normal vector to the uh, three coordinate faces are just minus, this is minus E1, minus E2, minus E3. And the inclined face normal might have three components, N1, N2, N3, right? This is something that hopefully, well, I know you guys did in the homework. A good relationship here is that area of the face that is in the minus E1 direction, right? This is minus E1, so this area I'm calling A1. This area is equal to N1 times AN, which is the first component of the normal times the area of the inclined face. Similarly, A2 is N2 times area of the inclined face. So these three relationships will help us simplify our equilibrium equations. And now we are ready to write the equilibrium equations, which, as I said, would be just sum of forces equal to 0. So sum of all the four tractions times their area plus the body force times their volume. That's all that we are going to do. So let's do that. On the face with normal negative E1, I have this minus T E1, write that. So minus T even face. What is the area of that face? Of this face, we just said that area is A1. Okay. So let me also, yeah. So A1 is the area minus T sub E2 times area A2 minus T sub E3 times area E3 and plus T sub n AN. That's the traction times area, traction times area, traction times area, traction times area for the four faces. That's the first part of that equation of equilibrium that I've written out. Plus body force times the volume. So the volume would be some, I'll keep that as Vn, but I'll write that as plus the body force B vector times V equal to 0. Okay, there's no other forces acting on this acting on this piece. I'll plug in these relationships. So if I do that, I get after some rearrangement T sub n minus n1 times T sub E1 minus N2 times T sub E2 minus N3 times T sub E3 and plus B times V, and I'm pulling out AN here, and let me see if I can move this a little bit. And divided by, sorry, I'll pick this out. V divided by AN equal to 0. So all I've done is just replace A1 with N1 times AN and pulled out AN outside. Okay, and on the last term, the term with B, I'm just multiplying and dividing by AN. So this AN is in the denominator. Now, the good thing is that as the size of this tetrahedron goes down to 0, when the size delta x, let's say, goes down to 0, can you tell me what the volume divided by area would tend to? Volume of the tetrahedron divided by area of any one of the inclined face, what would that tend to? So volume would be proportional to, let's say, delta x1 times delta x2 times delta x3, correct? Volume would have delta x cube type relation, whereas area would be delta x1 times delta x2. So what I'm saying is that volume is proportional to delta x cube, the area is proportional to delta x square. Okay. So when the size delta x itself tends down to 0, I have in the numerator delta x cube divided by delta x square, that will tend to 0. The body force will not contribute to this equilibrium equation when the size of this tetrahedron will be tends to 0. So all I'm left with is this bracketed quantity, Tn minus N1 T1 and minus N2 T2 and so on. Now, if you take a look at this next line that I've already written out here, all I'm doing is I'm writing out Tn on the left hand side and Te1 on the right hand side. So Te1 right here. N1 is nothing but the normal vector n dot product with E1, correct? Sorry, this should not be a vector, this should be a scalar. N2 is the second component of the unit normal to this inclined face. That unit normal can be obtained with the vector n dot with E2, similarly n dot with E3, and this E should also not be a normal, it's a scalar. So this just seems like a lot of algebra right now, but we'll come to something that resembles a stress tensor in a little bit. We also know that this expression can be written as T sub E1 dyad with E1 acting on N. You agree? Plus T sub E2 dyad with E2 acting on N, plus T sub E3 dyad with E3 acting on N. Do you agree that if this particular expression is just E1 dot with N and in the direction of TE1, which is up here. So the three terms written out here are nothing but expressing the same relationship in the form of a tensor. Now, obviously, since n is a constant, I can pull it out and collect these three bracketed terms together. And I will write that as sum of I going from 1 to 3 of T sub EI dyad with EI and acting on the vector n. And now I'm ready to assign some variable to this. I'm going to say that this is S acting on n, where the S is a stress, actually the Cauchy stress tensor. So let me call that thing in here. This is what I'm calling S, the Cauchy stress. And the name Cauchy stress is also important because there are different types of stress measures that we'll come up with maybe in the next couple of lectures. So this Cauchy stress is a very fundamental quantity when you are doing equilibrium. Once again, this Cauchy stress is coming from the free body diagram of this arbitrary point in a deformable body with a small neighborhood that we considered like a tetrahedron, and by doing just sum of forces, by relating the four tractions on these four faces, the body force contribution went to zero as delta x tended to zero. But the stress, what this allowed us to do was to correlate uh, a stress or a tensor type quantity with tractions. Tractions were our distributed forces, and what this relationship is saying is that go to any point in a deformable body. So I'll go back to this guy here. I have some deformable body. Go to any point in that deformable body, right, like here. Draw a small neighborhood of that point and consider some plane passing through that point at that inside that body. If that plane has a normal vector n, say this is the normal vector n to that plane, then the traction on that face is given by the stress, Cauchy stress tensor S acting on that normal, right? And this is another way to interpret that is again S, the Cauchy stress, is a tensor. Tensor acting on a vector gives me a vector, right? So the stress tensor acts on a normal vector to give me the traction vector. Just like the F tensor in our kinematics acted on undeformed normal vectors, undeformed tangent vectors to give me deformed tangent vectors for equilibrium. Stress tensor acts on a normal vector to give me the traction vector acting on that normal at that point. And this is a very fundamental relationship that you must always remember and understand how it works. And here's some more interpretation of that relationship. So let's say I want the three components of this traction vector acting on that inclined face n. So those three components would be T1, T2, T3 on the face with the normal n. That's what I'm writing out here. This equal to the T on face EI dyad with EI. What does that mean? This is nothing but the three components of the traction vector on any one of those faces. So let's say this face E1 dyad with EI. I hope you can see that EI is nothing but delta I1, delta I2, delta I3. So for example, if it is E1, then delta 1, 1 would be 1, delta 1, 2, delta 1, 3 would be 0. This is nothing but the expansion of this and times N1, N2, N3 with the normal components. And what that is represented by is the outer product of these values. So T1 is a scalar, T2 is a scalar, T3 is a scalar. Obviously, these three are scalars. This is a 3 cross 1 times a 1 cross 3, which gives me the 9 components of the stress tensor, of the Cauchy stress tensor. Okay. Those 9 components acting on 3 normal components give me the 3 vector components of the traction vector acting on that face. So, so this might take some time to digest, but essentially what you should understand is that the traction vectors at a point inside a deformable body in any arbitrary direction are captured by this stress tensor. If I know the stress tensor at a point inside a deformable body, you tell me any arbitrary face passing through that point, I can tell you what the traction vector would be acting on that face. Okay, that's simply by S acting on N. You give me N, I'll tell you what traction is on that face. Here's a few more physical interpretations of the components of this traction vector. Let's say my 9 components of the stress tensor are given in this manner, S11 to S33. If I take the stress tensor and act it on a face with normal E1, which is, this was minus E1. E1 would be obviously pointing in that direction. So if I want to find out what is the traction vector acting on a face that has normal E1, can you tell me what those components would be in terms of the components of the stress? That's right. So this is the stress tensor. All I need to do is to act it upon E1. E1 is nothing but 1, 0, 0, which will capture the first column of that stress tensor. So that will be S11, S21, S31. Similarly, traction on the face with E2 will capture the second column, 2, S22, S32. And finally, on the third face, S13, S23, S33. So essentially, the columns of this stress tensor, this, and this, these columns are nothing but the traction on the face with E1, traction on the face with normal E2, traction on the face with normal E3. That's what a stress tensor. That's what a stress tensor does. It correlates the tractions at a point inside a body in any arbitrary direction, and the components of the columns of that stress tensor matrix gives me the tractions on E1, E2, E3. All right. Couple more physical interpretations. We normally break up the traction on a surface into two components, a normal component and a shearing component. So let me talk a little bit about that. So for that, I will go back to this cubic infinitesimal neighborhood of a point inside a body. I have 6 faces here, and let's say that the resultant tractions, I can replace those resultant tractions with single vector arrows. So here I'm relying on your understanding that when the size of this cube shrinks down to 0, that traction on each of those 6 faces can be replaced with a constant traction. Okay. So those 6 arrows that I have drawn on the right hand side, this, for example, is the face with normal E2. The traction on that face could be pointing in some general direction, which I'm calling T sub E2. Similarly, on the opposite face, minus E2, there is a traction T minus E2. Let me ask you this. T sub E2 and T sub minus E2, is there some relationship between them? They should be minus of each other only when the size of this cube tends to 0, right? Because if the size of this cube is not 0, then we are not talking about the same point. So this would be equal to negative of this vector. And the same thing for all the other 4 faces, so total 6 faces. Now we also know the interpretation of the components of any tensor can be obtained by, we can pick out the component of any tensor, component ij by acting it on ej. That gives me some vector dot with ei. That would pick out the sij component out of these 9 components. And so if you go by that, interpretation, then you can clearly see that the second index j relates the columns of that stress tensor, correct? And the columns of that stress tensor are correlated with the traction vectors on the faces with normal E1, E2, E3. So essentially the second index here relates to the face that we are talking about, and the first index here relates to which component, 1, 2, or 3 within that face are we talking about. So Sij is the traction component. Just for example, let's say E1, I have traction E1 here. Clearly this has 3 components, something in E1, something in E2, something in E3. So if I break those components up, then the Second index represents the phase, which is E1. First index represents the component, that the direction of the traction that we are talking about. So that's one way to, another way to interpret the components of the stress tensor. And this figure right here on the right hand side is something that you've seen before. As I mentioned, stress is a tensor. It acts on normal vectors to give me corresponding traction vectors. And this figure is actually very important to understand, that we are again talking about, I can't stress this enough, that we have some, let's say, big concrete block. I go to the center of that block. Okay, that's a point completely inside that block. There, I can imagine infinitely many planes passing through that point. Those infinitely many planes have normal vectors associated with them, correct? Those are those green normal vectors that I'm talking about here. These green normal vectors. These represent normal vectors to infinitely many planes passing through a point inside or outside of a deformable body. The stress tensor at that point will act on any of these normals and will give me the corresponding traction vector acting on that face at that point perpendicular to that particular face that you've chosen. So what that means is that, for example, when we were drawing free body diagrams of these things, there is an imaginary cut that I've made, and there are infinitely many points over that cut surface. You must go to each and every point on that cut surface. There is a normal vector to the surface of the cut at that point. You take the stress tensor at that point, act it upon the normal vector, and that's what gives you the traction vector at that point on that cut. And that's what allows us to draw free body diagrams in the first place. Okay. So starting off with free body diagrams, we came to the definition of traction. From traction, we built up some equilibrium relationships, and finally derived this stress tensor, which acting on the normal gives me back the actual distributed forces acting on a free body diagram, kind of closing the loop here. Okay. All right, so I think that's enough for today to digest for you all. And we'll continue on Friday. For quiz 3, whatever we have covered up until now is going to be on the quiz. For the homework, you do need to find normal and shearing components of the traction, which actually is pretty obvious, but I'll let you take a look at that. Otherwise, I'll continue covering that on Friday. Okay.